Hi, welcome to Module 4, Machine Learning for Fine-Tuning of Quantum Dots. So in the previous 3 modules, we built up the rough tuning, sort of finer charge tuning, then we looked at some unsupervised technique, and now we will look at the really final step in this hierarchy, which is the really small kind of tuning you need during the operation of your device. The structure of this module, as per usual, I will start by talking a bit more about what's the motivation for fine-tuning, what it is, why do we need it. Then we will zoom into a very concrete example as always. This time is going to be something called Overhauser field estimation. I'm going to explain to you what it is later on in the module. Then I'm going to give a little bit more longer look at what is the state of fine-tuning in real experimental setups, and then you will conclude with a coding demo with Tin. She is going to walk you through the fine-tuning Overhauser field estimation code so you can redo everything you learned today for yourselves. So let's get started with the motivation for fine-tuning. So far, we arrived to the point in the course where you successfully rough-tuned, charge-tuned, and your qubits are ready to go. So it could seem that what is left is just to celebrate and enjoy your qubits, but there is still a module 4, so maybe that's not the final answer. The reality is that even when you really define the operating regime of your device and you prepare, for example, a specific charge state that you want to be in, you still have to do some extra tuning to sort of stabilize your qubits or your device state in the operating regime where you want to be in. Now, the way you do this is super diverse and really heavily depends on exactly what kind of experiment you are doing, because the stabilization with respect to which exact phenomena is going to pretty dramatically influence exactly what you need to do. These are just 3 examples in a whole zoo of something that could be, to a reasonable degree of approximation, considered a fine-tuning. For example, you need to probably watch out your tunneling rates. So since you prepared your wonderful qubit states, you don't want to have some losses and start all over again with your tuning. Another possible aspect is that you narrow down everything in terms of voltage space, but you still have some kind of physical phenomena that might be influencing your device operation, in which case you want to learn what it is or what is the magnitude of the phenomena or frequency or anything like that. This can be seen as a Hamiltonian learning or underlying physics learning, and it's something that we are going to concentrate the most on today. And then the final example is that of if you are really far with your experiments and you are really operating in the regime where you want to actually do quantum gates, you want to implement some quantum algorithm. Again, your setup is not going to be completely static. There will be crosstalk and other effects. So whenever you do some quantum operations, probably there will be some accumulated phases. Other qubits are going to feel what you're doing. So tuning quantum gates could be another example of this kind of stabilization of your device in the regime when you want to operate it in. In the end, as I mentioned previously, this is really a most complex layer of tuning due to the experimental diversity that there is, because the stabilization will look super different based on what kind of experiment you are exactly doing. So this is the slide that you saw before, and in the module 1, where we sort of advertise that we will operate on a different abstraction level. On a dark blue level was the machine learning for tuning, where you use a machine learning to directly navigate some features in your data, like searching for charge transitions. And by now, you are experts on that, and you can do that in many different problem settings very, very easily. What we want to do now is to lift a layer up and go to the light blue block, where we will be learning an underlying physics. From a machine learning point of view, this is not at all different. You will again be taking data and mapping them on something. But from a sort of intellectual point of view, this is usually harder to understand, because you want to map your data not on a decision, shift the voltage right. You want to map your data on some parameter that really governs your underlying physics. So this is really important to have in mind, that this is sort of different conceptual goal that we have in mind today in a module 4 compared to the modules 1 to 3. Specifically, we are going to concentrate on something called Hamiltonian learning. You saw a slide like this also earlier in the lecture. Again, the problem setting is that you will measure whichever data you want to measure in whatever setting you have, whatever is accessible to you. You will run it into the machine learning model, and then you will output something, and that something this time will be key parameters of your Hamiltonian. So now we are not doing shifting voltages decision or classifying charge stability diagrams. Now we want to know what is the Hamiltonian term that governs the physics that allows us to measure whatever we are currently measuring. So this is again really the sort of conceptual difference compared to the previous things we discussed. But from a machine learning point of view, it's very similar, because it's again data, model, some kind of numerical output.